100 years ago, how many subatomic particles were known to mankind? The electron, the proton, and maybe if you include the photon. These are the particles that were known almost 100 years ago. But in these 100 years, we have studied extensively particles like neutrons, pi mesons, muon particles, tau particles, sigma particles, omega particles, xi particles, lambda particles, and on and on and on. We have found out that there are indeed hundreds and hundreds of subatomic particles out there, and associated with these hundreds of subatomic particles is a huge diversity of particle interactions. So we have hundreds and hundreds of particles out there and hundreds and thousands of particle interactions or reactions or particle decays, however you may want to call them. So you end up getting a chaos of a diversity of particle interactions. So it becomes very important for us to understand or seek whether or not there are rules associated with these kind of particle interactions. And as it turns out, based on studies of a large number of particle interactions in the last 50 to 100 years, scientists have found that we can associate certain numbers or quantum numbers with a certain class of particles that remain conserved whenever particle interactions happen. Now, we already know about conservation laws like energy, linear momentum, angular momentum, and electronic charge, etc., etc. Apart from those conservation laws, as it turns out, when we are talking about interactions of elementary particles, then those interactions happen in such a manner that we can associate a certain set of numbers, namely the Lepton quantum number, the Baryon quantum number, and the Strangeness quantum number, which, as it turns out, is conserved in certain kinds of interactions. And understanding that will give us an idea about what kind of particle interactions are allowed in nature, what happen in nature, and which of them do not happen in nature. So in a way, in this chaos of different kinds of particle interactions, you will have a little bit of an idea of which of them are allowed, which of them are not allowed. You will get a little bit of a confidence in this whole chaos of particle interactions. So that is what I'm going to talk about today in this video. So let us first talk about the Lepton quantum number. So the Lepton quantum number is a number that we can associate with particle interactions that involve lepton particles. Now, what are lepton particles? These are elementary particles that do not experience the strong force. Essentially, they consist of 6 particles: the electron, the muon particle, tau particle, and their associated neutrinos, the electron neutrino, muon neutrino, and the tau neutrino. So there are 6 particles and their antiparticles which comprise the lepton particles. Now, if you are interested in knowing more about leptons and their properties, I have made a video discussing leptons extensively. You can check out that particular video. Here I'm going to talk about particle interactions that involve these lepton particles. So the lepton particles either induce some kind of a particle reaction or they are the result of some kind of a particle decay. Now, as it turns out, whenever these particle interactions are taking place, we can associate a number with these lepton particles such that it turns out that these numbers, when added together before and after the interaction takes place, remains conserved. So before I talk about a couple of particle interactions, let me first define the values of these numbers. Okay, so I have 3 numbers: the electron lepton number associated with the electron family, the muon lepton number associated with the muon family, and the tau lepton number associated with the tau family, each distinct from one another. And we can associate values of 1, -1, or 0 for all particles. Okay, so as it turns out, the electron lepton number has a value of 1 for the electron, It has a value of 1 for the electron neutrino, but it has a value of -1 for their antiparticles. So it has a value of -1 for the anti-electron, and it has a value of -1 for the anti-electron neutrino. All right, let me repeat it again. The lepton number for the electrons has a value of 1 for the electron as well as the electron neutrino, but it has a value of -1 for the anti-electron as well as the anti-electron neutrino, while it has a value of 0 for all other particles. Similarly, we can associate a muon number which has a value of, in the same way, 1 for the muon particle and the muon neutrino, but it has a value of -1 for the anti-muon particle and the anti-muon neutrino. All right, and it has a value of 0 for all other particles. Similarly, the tau number can have a value of 1 for the tau particle and the tau neutrino, but it has a value of -1 for the anti-tau particle and the anti-tau neutrino, while it has a value of 0 for all other particles. So even though these three numbers are distinct from one another, their values could be similar: 1, 0, -1, right? 1 for the particles, -1 for the antiparticles, and 0 for everything else, right? So for the electron-lepton number, you have 1 for the electron and the electron neutrino, -1 for the anti-electron and the anti-electron neutrino, 0 for all others. Similarly for the muon lepton number and the tau lepton number. Now we can use these numbers in different kinds of particle interactions to see that they do indeed remain conserved. Okay, so here is a bunch of particle interactions that do happen in nature which involve lepton particles, and based on what we just now discussed, let's see if we can associate the lepton numbers that I talked about in these reactions and see whether or not they are conserved. Okay, so let's first start with this reaction here, or this interaction, which is nothing but the negative beta decay reaction, in which case a neutron becomes a proton, leads to the emission of an electron or the beta particle and an electron antineutrino in the process. Now this interaction involves electron and electron antineutrino, right? So in this case, I'm only going to look at the lepton number for electrons or the electron number, right? So what is the electron lepton number for a neutron and a proton? They are nothing but 0, all right? For all other particles, they are 0, right? Remember? But for the case of an electron, it is 1. For the case of an electron antineutrino, it is -1. Now these quantum numbers are additive in nature, additive in the sense that you can add these quantum numbers in the left hand side and the right hand side, and you can see whether or not that particular summation is conserved or not. So in the left hand side, the lepton quantum number has a value of 0. On the right hand side, it has a value of 1 - 1, which is nothing but 0. That means in this case, this is conserved, right? Now let's go ahead to the next interaction, which is the positive beta decay, in which case a proton becomes a neutron, leads to the emission of a positron, which is an anti-electron, and also an electron neutrino in the process. So if I look at the same electron lepton number for a proton and a neutron, they turn out to be 0, right? But for the case of an anti-electron, it has a value of how much? You remember? -1, yes? But for the case of electron neutrino, it has a value of +1, right? Again, left hand side, it has a value of 0. Right hand side, the summation of these two numbers has a value of 0. That means the lepton quantum number for the electrons in this case is conserved, right? Let's go ahead to the next. So this is a case of a decay involving a pi meson. So free pi mesons can decay into muon particles and lead to the emission of a anti-muon neutrino. This interaction does not involve either electrons or electron neutrinos, but it involves muons and muon neutrinos, right? So we are going to look at the muon number in this case. Okay, so what is the muon lepton number for a pi meson? It is 0. What is it for a muon particle? +1, remember? And what is it for a muon antineutrino? It is -1. Again, muon lepton numbers are additive, that we look at the sum on the left hand side and the right hand side. So on the left hand side is a value of 0, right hand side is a value of 1 minus 1, 0. Again, the muon lepton number is conserved. Now what happens to a muon particle once it is formed? A free muon particle can decay into an electron antineutrino, and a muon neutrino. Now this kind of an interaction involves both the particles from electron family as well as from the muon family. So we need to check them separately, because I told you that the electron number, the muon number and the tau number, they are distinct, and we need to check their conservation separately. So first we will check their conservation associated with the electron lepton number, and then we will check the conservation associated with the muon lepton number. So what is the electron lepton number for a muon particle? It's 0. Right. What is the electron lepton number for an electron particle? It's +1. For an electron antineutrino, it's -1. For a muon neutrino, it's 0. Right. It is conserved. Left hand side 0, right hand side summation of 1 minus 1 comes out to be 0. Now let's look at the muon lepton number. What is the muon lepton number for a muon particle? It's 1. What's the muon lepton number for an electron particle? It's 0. What's the muon lepton number for an electron antineutrino? It's 0. And what's the muon lepton number for the muon neutrino? It's 1. It's conserved, right? Left hand side 1, right hand side 1. So these quantum numbers are additive. That means you can add them on the right hand side as well as on the left hand side, and you can check for their conservation. Now once you get to know about the electron lepton number, muon lepton number, it gives you an idea about what sort of interactions are possible and what sort of interactions are not possible. Because sometimes in examinations you are asked questions about okay, complete this particular reaction, or tell us whether or not this reaction is possible or not possible. And once you get an idea about this, then you can get an idea about which of the reactions are possible and even predict which particle is going to involve. So let me give you an example. I'm sure that every time you studied beta decay, you were confused at one point whether along with the electron, an electron antineutrino was emitted or an electron neutrino was emitted. I'm sure most of you were confused at some point. So in this case, if an electron is emitted along with an electron antineutrino, you get 1 and 1 lepton number, which remains conserved, right? But is this reaction possible? Can an electron be emitted with an electron neutrino? Because if an electron is emitted with an electron neutrino, the lepton number will be +1 and +1 in both cases. Left hand side 0, right hand side +1 + 1 equals 2. Violation of the conservation of lepton quantum number. It's not possible. This reaction does not happen. This is not allowed in nature. So electron will never be emitted along with the electron neutrino, but it will only be emitted along with the antiparticle of the electron neutrino. So the antiparticle of the electron neutrino is this, which is a lepton quantum number of -1. This reaction is possible. Same for the case of muon and the anti-muon neutrino, right? And whenever one of these particles like muons decay, in that case on the other side you can have a muon neutrino, because in that case the quantum number remains conserved. So I hope that this gives you a little bit of a clue as to what kind of particles are involved, because as a student even I got confused in the examination when I used to think like, okay, with the electron, will the electron neutrino be emitted or the electron antineutrino? This is something really confuses you, right? So once you understand this, now it makes sense. Along with the electron, always an electron antineutrino is emitted. Along with the muon, always an muon antineutrino is emitted, right? Same with the positron. Along with the positron, electron neutrino is emitted, right? Let's go ahead to the next interaction. The tau particle can decay under certain situations into a pi meson and a tau neutrino. So we will only look at the conservation of the tau lepton number, which is L tau. Now what is L tau for the tau particle? It's 1. What is L tau for the pi meson? It's 0. And for the tau neutrino, it's 1. Conserved, right? Left hand side 1, right hand side 1. The tau lepton number is conserved. And the last interaction I have is the tau particle can sometimes also decay into an electron antineutrino and a tau neutrino. Again, here we have two family of particles, electrons and the tau particles, right? So we need to check their conservation separately. So first we will look at the electron lepton number, which is a value of 0 for the tau particle, 1 for the electron, -1 for the electron antineutrino, and 0 for the tau neutrino. And then we have to check for the tau lepton number, which is a value of what? 1 for the tau particle, 0 for the electron, 0 for the electron antineutrino, and 1 for the tau neutrino. Again, as you can see, these numbers are conserved in the left hand side and the right hand side. So as it turns out, when we associate the electron family, the muon family, and the tau family with these distinct lepton numbers, the electron number, the muon number, and the tau number, then it turns out that these quantum numbers are conserved in different kinds of particle interactions involving these particles. So in a way, this gives you a set of rules that will help you get an idea about what kind of particle interactions are possible, what kind of particle interactions are not possible. So lepton quantum number is always conserved except maybe in neutrino oscillations. So in neutrino oscillations, lepton quantum number is not conserved as a particle goes from one point to another, but apart from that, in almost all other particle interactions, the lepton quantum number is conserved. So this gives you a very helpful tool in sorting out different kinds of particle interactions. Now let's move ahead to the next quantum number, which is the baryon quantum number. So the baryon particles are essentially particles that consist of 3 quarks. Now remember, I talked about leptons as those elementary particles that do not experience the strong force. Now as opposed to leptons, there is a class of particles called hadrons, which are particles that do experience a strong force. And the hadrons can be further classified into what is called baryon particles and meson particles. So baryons and these meson particles belong to a category called hadrons. I have talked in detail about these particles in one of my earlier videos. If you're interested, you can check that out. So as it turns out, these baryon particles, whenever they are involved in some kind of a particle interaction, then we can associate a similar kind of a number with them such that that particular number, its summation, remains conserved whenever particle interactions happen. So a very simple rule is as follows. So all baryons, so baryons are basically like neutrons, protons, lambda particles, omega particles, sigma particles, xi particles, etc. Right? So it consists of the nucleon particles as well as the hyperon particles, which consist of 3 quarks essentially. Okay, they do not include the mesons. Mesons basically have 2 quarks in them, so they do not include the mesons. They only include the baryons, which basically include 3 quarks inside them. So all the baryons have a number of equal to 1 that we can associate with them. This is called the baryon number, represented by the capital B. And the anti-baryons, like the anti-neutron, the anti-proton, as well as the anti-particle version of the rest, can be associated with a number of -1, while the rest of the particles can be associated with 0. So +1, -1 and 0 for the baryons, anti-baryons, and for the rest we can associate with these particles and look at their conservation in different particle interactions. So the baryon number essentially of 1 basically comes out as a result of the quarks. Okay, so we can also say that the quarks have a baryon number of 1/3, while the anti-quarks have a baryon number of -1/3. Okay, so because baryons are made up of 3 quarks, so 1/3 plus 1/3 plus 1/3 come out to be equal to 1, while mesons on the other hand are made up of a quark anti-quark. So a baryon number of 1/3 minus 1/3 comes out to be 0. So mesons have a baryon number of 0, baryons have a baryon number of +1. Let's look at a few interactions. Okay, so here again I have this interaction, which is the beta decay interaction. So a neutron becomes a proton, leads to the emission of an electron and an electron antineutrino. So if I look at the baryon number here, so the neutron and a proton are baryon particles, so they have a value of 1 each. All right, the other two have a value of 0. So as you can see, the left hand side is a baryon number of 1, right hand side is the baryon number of 1, so this number remains conserved, right? So if there is a baryon particle on the left hand side, there must be a baryon particle on the right hand side. In certain kinds of high energetic reactions, a proton and a neutron may collide under extreme energy and lead to the creation of new particles like this. So let's look at this kind of a reaction. So the baryon number for a proton and a neutron is equal to 1, right? On the right hand side you have a proton and a neutron and a proton and an anti-proton which has a value of -1. So what is the value of baryon number left hand side? 1 plus 1, 2. On the right hand side, you have 1 plus 1 plus 1, 3 minus 1, 2. So 2, 2. That means this number is conserved in this kind of a particle interaction. Now, as it turns out, baryon number is a kind of a quantum number that is conserved in different kinds of particle interactions. So getting an idea about this number will give you an idea about which of the reactions are possible or not possible whenever baryon particles are involved. And last but not the least, there is another quantum number which is known as the strangeness quantum number. This is called strangeness quantum number because it is associated with particles that has a different kind of a, what you can say, strange behavior. So scientists, when they were looking at different kinds of interactions in the last 100 years, around 1950s or 60s, they found that there is a large number of particles which were created that behaved in a very strange manner, that were produced by either strong or electromagnetic interaction, but that decayed via weak interaction. And those particles scientists named as strange particles. And there is a quantum number associated with those particles also, which is known as the strangeness quantum number. Okay, so almost half a century ago, scientists were studying the creation of newer and newer particles, right? So whenever you look at cosmic rays, when they enter the Earth's atmosphere, it leads to the creation of a large number of subatomic particles. Or whenever you study high energetic particle interactions in particle accelerators, you end up getting newer and newer particles. So when scientists were studying the byproducts of extremely high energetic particle interactions, then they found out that newer and newer particles were being created that behaved in a very strange manner. That is why this number is called strangeness number. So they behaved in a strange manner in this particular way. They were created via electromagnetic or strong interaction, but after they were created, they decayed via weak interaction. So these strange particles are subatomic particles which are created via strong interaction or electromagnetic interaction, but they decay via weak interaction. Now, as it turns out, when we study these kind of strange particles, we can associate a quantum number known as the strangeness quantum number with these particles that remain conserved at least in their creation, if not in their decay interactions. So before I talk about the interactions specially, let's look at different kinds of particles. Okay, so here I have a bunch of what is called hadron particles. Okay, so the essentially the strangeness quantum number is a result of the strange quark. So you see the hadron particles are made up of quarks, right? Mesons are made up of 2 quarks, baryons are made up of 3 quarks, and there are different kinds of quarks. You have up quark, down quark, strange quark, charm quark, top quark, and bottom quark. The strange behavior of these particles are essentially for those particles that contain what is known as the strange quark. So hadron particles that do not contain the strange quark, like neutron, proton, and pi meson, they have a strangeness number of 0. All right, but let's look at the lambda particle. So lambda particle has a strangeness number of -1. This is because its configuration has 1 up quark, 1 down quark, and 1 strange quark. So essentially all the quarks have a strangeness number. So the strange quark has a strangeness number of -1. The rest of the quarks has a strangeness number of 0. Okay, so the strangeness number is associated with the strange quark, which has a value of -1. The other quarks has a strangeness number of 0. And on the other hand, the antiparticle for the strange quark has a value of +1. Okay, so whenever you have hadron particles created by the strange quark, you end up getting some kind of a strangeness number. So the lambda particle which contains 1 strange quark has a strangeness number of -1. Similarly, you can have sigma particles, sigma plus, sigma 0, sigma minus. So superscript basically tells us about the charge. It also has a strangeness number of -1 because if you look at their configuration, they contain 1 strange quark each. Okay, so this is the configuration for sigma plus, this is the configuration for sigma 0, and this is the configuration for sigma -1. Now if you look at the Xi particles, Xi 0 and Xi -1, they have a strangeness number of -2 because they contain 2 strange quarks. The Xi0 has up quark and 2 strange quark, and the Xi minus has 1 down quark and 2 strange quark. So it has a strangeness number of -2. And on the other hand, the omega particle, which contains 3 strange quarks, so the omega minus is composed of 3 strange quarks, has a strangeness number of -3. Now, apart from these baryon particles, the pi meson as well as other meson particles can also have a strangeness number. The pi meson is not made up of a strange quark, so it has 0. But what about kaon particles? Kaon particles are mesons. That means they are made up of 2 quarks. So K0 is made up of 1 down quark and 1 anti-strange quark, while K plus has 1 up quark and 1 anti-strange quark. So the anti-strange quark has a strangeness number of +1. Okay, so these two particles have a strangeness number of +1. On the other hand, K minus will have a strangeness number of -1. So the strangeness quantum number is conserved only in those cases which involve either the electromagnetic interaction or the strong interaction. So interactions which involve electromagnetic force or the strong force, only in those cases the strangeness number is conserved. But whenever we look at decay processes where the particle may decay into further particles, in those cases where a weak interaction is involved, the strangeness number is not conserved. It may change if it involves the weak interaction. So let's look at a few examples. So for example, here I have two interactions that involve a mediation by either a strong force or an electromagnetic force, right? So in these cases, strangeness number is conserved. So a proton and a proton may collide in particle accelerators to create further particles, like let's suppose a lambda naught, kaon naught particle and a proton and an anti-pi meson. Okay, so if this kind of an interaction is happening, let's say we want to check for the conservation of strangeness number. So we can apply these numbers that I've associated with these different particles and put the values there to see what's going to happen. Now, before I apply the strangeness number, let's apply first the baryon number, right, which I discussed earlier. So baryon number for a proton is 1, right? In the case of a proton, it is 1, right? Now the lambda naught is also a baryon particle, so that also has 1. K naught is a meson particle, so it has a baryon number of 0. Pi plus is a meson particle, so it is a baryon number of 0. Now if you look at the strangeness number, protons have a strangeness number of 0, right? The lambda naught has a strangeness number of -1, okay? K naught has a strangeness number of +1, all right? Proton has a strangeness number of 0, and pi mesons have a strangeness number of 0. So as you can see, the baryon number is of course conserved, left hand side 2, right hand side 2. The strangeness number, left hand side 0, right hand side 1, -1, 0. So the strangeness number is also conserved in this particular case. Now let's go ahead and look at this next interaction where a pi meson or an anti-pi meson interacts with a proton to create this kind of a sigma particle and a kaon particle. Okay, so again I can associate the baryon number here. So the baryon number of a pi meson is 0, for a proton it's 1. For a sigma particle it's 1, for a kaon particle, which is nothing but the meson, it's 0. And the strangeness number for a pi meson is again 0, for a proton is again 0, for a sigma particle is -1 here, and for a K plus particle is again +1. So as you can see, the baryon number is 1 left hand side, 1 right hand side, it's conserved. So strangeness number is 0 left hand side, 0 right hand side, it's conserved. So in these interactions, which are usually mediated by either a strong interaction or an electromagnetic interaction. So a proton and proton colliding is basically a strong interaction, and it also involves electromagnetic interaction. And same goes for the next one. In these kind of cases, the strangeness number is usually conserved. But if we look at particles like the baryon particles decaying via weak interaction, so if a strange particle decays via weak interaction, then in those cases the strangeness number is not conserved. So again, let's look at a few examples. So here we have a couple of interactions that involve decays of strange particles via weak interactions. Now as it turns out, in weak interactions the strangeness number is not conserved. Okay, so if you look at this particular interaction where xi particles becomes a lambda particle and a pi meson, so if you look at the strangeness number, as it turns out, the xi particle has a strangeness number of -2, right, while the lambda particle has a strangeness number of -1, and pi meson has a strangeness number of 0. So what is the change involved here? So what is this change in the strangeness number? So -2 becomes -1, so it is +1. So the overall the strangeness number changed by a value of +1. The lambda naught particle may further decay into a neutron and a neutral pi meson. So in this case, the strangeness number will have a value of -1, right, and 0, 0. Okay, neutron and pi meson have values of 0, 0 for strangeness number. So in this case also, left hand side -1, right hand side 0. So there is a change in the strangeness number by +1, right? In the last case, we have the sigma particle, which also has a strangeness number of -1. It becomes a lambda particle, which has a value of -1, and a gamma photon, which is a strangeness number of 0. In this case, however, the strangeness number did not undergo any change. So there is a change of 0. Left hand side also -1, right hand side also +1. Left hand side also -1, right hand side also -1. So as it turns out, in the case of weak interactions where strange particles or particles that involved a strange quark undergo decay via weak interactions, then we cannot definitely say that the strangeness number is going to be conserved. In some cases it is conserved, in some cases it is not conserved. They may change by either +1 or -1. So that is all. This lepton number, baryon number, and the strangeness number are basically a set of rules based on studies over the last 50 years, which gives us an idea how different kinds of subatomic particles interact. All right. So out of all the chaos and diversity of different particle interactions, we have got some idea about these numbers that helps us get some confidence about what is happening and what sort of interactions are happening, what sort of interactions are allowed, what sort of interactions are not allowed. So before I finish the video, I want to do a little bit of a test. Okay, so I'll give you a couple of interactions, some of which are allowed, some of which are not allowed, and you tell me whether or not they are possible or not based on what we just now discussed. Okay, so I have here a couple of particle interactions, some of which are possible in nature, some of which are not possible. And think of this as a kind of a test based on what we just discussed in this video. Can you determine which of these are allowed, which of these are not allowed, which of these happen in nature, which of these do not happen? So let's look at them one by one. Okay, so let's start with the first interaction. A tau particle becomes an electron and leads to emission of an electron neutrino and tau neutrino. Okay, here we have to check the electron number and the tau number. So if you check the electron number, it turns out to be 0, 1, 1, 0, right? If you look at the tau lepton number, it comes out to be 1, 1, 0, 0. So the tau lepton number is conserved, but the electron lepton number is not conserved. The electron is being emitted along with an electron neutrino, which is not possible. So this is a reaction which does not happen in nature. Let's look at the second one. A tau becomes a muon, and a muon antineutrino and a tau neutrino is produced. So we'll have to check the muon number as well as the tau number. So the muon number is 0, 1, for the anti-muon neutrino -1 and 0, right? The tau number is 1 and 1, 0, 0 here. Can you see? Can you figure it out? So the muon number is conserved, 1 minus 1, 0. The tau number is also conserved. This is possible. See, right? The next is simply pair creation. A gamma photon becomes an electron and a positron. So if I look at the electron lepton number, the gamma photon has 0, electron has 1, and positron has -1. Electron lepton number is conserved. This is allowed. So this is something that is allowed in nature. Let's look at the next one. A muon antiparticle becomes a positron, and electron neutrino and anti-muon neutrino is emitted in the process. So here we'll have to check what? The muon number and the electron number, right? So let's look at the electron lepton number first. It is 0, -1, 1 and 0, right? For the positron, the electron lepton number is -1. For electron neutrino, it is +1. Now what about the muon lepton number? It is -1 because mu plus is the antiparticle of a muon, all right? And the anti-muon neutrino is also -1 and 0, 0 here. So here it seems that both are conserved, -1, -1 here for the muon number and -1 + 1, 0 for the electron number. So this is an interaction which is allowed. Let's look at this one. This consists of protons and neutrons. So we'll have to check for what? We'll have to check for the baryon number in this case. Okay, so a proton and a neutron under high energetic interaction leads to the creation of a proton and neutron and an antiproton. All right. So if you look at the baryon number for a proton and neutron, it's 1. Proton, neutron is 1. Antiproton is -1. Left hand side 2, right hand side 1. This does not lead to the conservation of baryon number, which is not seen in nature. Okay, baryon number is always conserved. So this reaction is not possible. Now let's look at the next one. Now this involves not only baryon particles but also strange particles, the hyperon particles that contain strange core. So we'll have to look at baryon conservation as well as strangeness conservation. Okay, now because a meson and a proton are interacting, so this is a strong interaction. So I expect that strangeness number should be conserved if this reaction does indeed happen in nature. So first let's look at the baryon number. So baryon number for a pi meson is what? 0. For a proton is what? 1. Lambda naught is a baryon particle, so it's 1. Kaon is a meson particle, so it's 0. Okay, let's look at the strangeness number. Strangeness number for a pi meson as well as a proton is 0 and 0. The strangeness number for a lambda is -1, but for K naught it is +1. So the strangeness number is conserved. Okay, -1 + 1, 0 right hand side, 0 left hand side. So this indeed is a interaction that is allowed in nature. Now let's go to the next one. A antiparticle for a pi meson, so the anti-pi meson becomes an anti-muon and leads to the emission of a muon neutrino. So here we'll have to look up muon lepton number, right? So the muon lepton number for a pi meson is 0, for an anti-muon is -1, and for a muon is 1. So this muon lepton number is conserved. This is allowed. Now let's look here. Here we need to check both the lepton numbers for electron as well as the baryon number. So the baryon number is 1 and 1 is conserved. Okay, but what about the electron lepton number? Electron lepton number for a proton is what? 0. Neutron is what? 0. What is the electron lepton number for a positron? -1, right? What is the electron lepton number for an anti-electron neutrino? -1, right? The electron lepton number is not conserved. Left hand side is 0, right hand side is -2. This is not possible. So a positron and an electron antineutrino will not be emitted together. Okay, electron can be emitted with an electron antineutrino and positron can be emitted with an electron neutrino, but this is not going to happen. So this is a reaction that does not happen at all. Finally, we have this kind of a kaon particle. Proton leads to a xi particle and another k naught. All right, so here we'll have to check the baryon number. The baryon number is 0 for k naught, k minus, which is a meson particle, 1 and 1 and 0. Okay, so the baryon number is conserved. But what about the strangeness number? The strangeness number for k minus is basically equal to -1. For a proton is equal to 0. For a xi particle, if you remember from my table previous that I have showed, is -2, and for k naught is basically equal to +1. So strangeness number is -1 left hand side, and -2 + 1 is also -1 right hand side. So strangeness number is also conserved, and I see that this is a strong interaction, so therefore this reaction is possible. So as you can see, here I had a set of different kinds of particle interactions, and by applying the lepton number conservation, the baryon number conservation, and the strangeness number conservation for strong interactions, I can figure out which one of them are allowed and which one of them are not. So in a sense, these quantum numbers give you an idea about which of these particle interactions do indeed happen or not. So in a way, giving you a clue, a kind of a confidence in the chaos of particle interactions. So that is all for today. Thank you very much.